Swayam Prabha. Digital India. Educated India.
Okay, so let's get started. So in this one, we will we will do the active learning thing. Hopefully, you guys are able to reach here. Same Google Drive link that was shared earlier. In that, you will find the presentation as well as the hands-on tutorial there. Again, this is based on this particular paper, archive paper, which is mentioned here. These are the libraries. I think now you guys are familiar with all of this. Okay, so I'm not talk too much about it. Yeah. So we'll start with first identifying what is my training data. There is always a known data set, which is my training data, for which x and y both are known, and then I have a candidate data set for which only x is known, and I want to make predictions. Okay, so I am loading my training data here. Should I make it more larger or is it okay? Fine. Okay. So now one thing I have done is yeah, so this is how my training data looks like, which has just 25 rows. So only 25 materials I am starting with. Okay. So see how small my training data is. And then I am downloading my candidate data set. I think this should be n equals to 25. Okay, so this is the training, the candidate data set, which is about 600 candidates in them. Okay, this data set is about band gap, if I am remembering it correctly. So if we go towards the end of this training, I don't see how can I go that side. EG, so it should be band gap. Yeah. So this is about band gap. I'm not able to go that side. Scroll, I don't know how to in this one. There. Okay. Yeah. So experimental band gap data is available to us as the last column. Okay. Okay. So this one, it should be n equals to 25. So training data set is 25 and candidate data set is about 600. Actually, the way I have done it is I have a training data set which is 500 and then a candidate data set which is 1600. But from that 500, I am only using 25 of those to make sure that I have a very small data set. Okay. The reason these two are there, because my candidate data set will be separate and training data set will be totally separate. There is no overlap between them. Okay. What are the type of features we are using? What do you guys think? What are the type of features we are using? Elemental features, that high level features which are basically some other physical properties being used to learn some other physical property. Okay. And then I just went ahead and did my training test plate. I think I forgot to run previous one. Okay, I think in this case, yeah, so training data, and this is my current best. Current best is nothing but maximum of the current training data that is available to me. So the best candidate I have is having a band gap of around 3.63. And the way I am posing the problem is I want to find a material which has the highest band gap. Okay, that's what I want to do. So then we go ahead and train our GPR model. So I've just created a function that will create the GPR model. Kamal talked about creating pipeline. So this is one small example of creating the pipeline. And then you remember there was a little bit complicated looking formula for expected improvement, which has the cumulative distribution function, the PDF function. So this is my function that basically computes the expected improvement. Okay, so that formula is being computed within this function. Okay, yeah. Yeah, so some hyperparameter tuning may be happening inside this GPR function. Okay, so within this one line, basically you did your hyperparameter tuning, the GPR model is trained. Okay, so again, this one line is encompassing whatever you have learned so far in the last 3-4 days. You try out. In here, I am directly using GPR. It's not necessary. You can come up with other methods. The only requirement is uncertainty and mean both should be given. The output should not be a point estimate but a distribution. Okay. These are your CV results, and then I am just plotting the parity plot. Okay. So, okay, the main thing starts from here. Now what I want to do is I want to compute the expected improvement for the candidate pool. That expected improvement formula that you saw, that I want to apply for all the candidates. My model is trained. Okay, I want to apply that formula for all my candidates. And if you remember, there was a trade-off that that eta symbol was there, which was your trade-off between exploration, exploitation. That value I have chosen it to be 0.1. Okay.
What is its range? Trade-off 0 to 1?
So trade-off in this particular case, this one is in the same space as that of your property. Okay. So depending on your scale of property is how you need to manage this trade-off. So say you are in Vickers hardness scale, so you have to accordingly change this trade-off value.
The more it is, the more will be the exploration.
The more the value of trade-off, the more will be the exploration. So in this one, what is happening? Let's see. I am doing model.predict on my entire candidate set. So basically, I get 1600 or so predictions along with their standard deviation. So variance and prediction is there with me. I also do model.predict on the training data set just to get y-train and y-train standard deviation. And then I am applying that formula, the same function that I show you. I am just showing it once here. And then I apply this formula for entire candidate set, and it's being plotted. So on the x-axis are my 1600 candidates. On the y-axis, color in Z, this should be band gap. So it is incorrect here. This should be band gap. So the color in green is telling me the mean value, basically the band gap, predicted band gap value. And the blue thing is telling me expected improvement. Okay. So it's very hard to see. Basically what I am trying to say is for all candidates you have a mu cap and an expected improvement value. So just we'll just visualize the top first 50 candidates to get a sense, right? That 1600 is too many things visualized together. So I am looking at just now the first 50 candidates. Blue is again the expected improvement and green is my band gap prediction, predictive band gap. Okay. Do you guys see the error bars? Okay. Now tell me which are the points which are resulting in high expected improvement. What are the type of points which result in a high expected improvement? Okay. Can you give a number so that we can? Around 8. So 10, this one, left or right? 6, this one, yeah. Oh, okay, so okay, I cannot, yeah. So look at this point, okay. What is my current best? What was my current best? 3 point something, right? 3 point something. What is the predicted value? Okay, very low, much lower than my current best value. Okay, but still the expected improvement is actually large. Okay, so why the expected improvement is large? Just think about it, right? I have a prediction for which the value is much lower than the training data set. but still the expectation that the improvement will be there is large. How is that the case? The uncertainty is very large, right? Although the prediction from the model is low, but the model is also saying that prediction is low, but I am not at all confident. It may be very large also. So again, going back to the previous lecture, my expected improvement is a trade-off between both. I mean, it's a balance between both exploration and exploitation. The reason this expected improvement value is large is because the uncertainty is large. Okay. Any other point? 40. Let's look at 40. Okay, this point. Left or right? Okay, left. So same thing. Expected improvement is still high, but the uncertainty, I mean the mean value mu cap is low, but uncertainty is very large. Okay.
What about 45?
Okay, let's look at 45. This one? Left or right? Right. This one. Okay, this expected improvement is very low. Why is that the case? Mu cap is low. At the same time, the uncertainty is low, meaning my model is saying definitely this point will have low band gap. And so your expected improvement for such a case should be low, right? The model is confident that the prediction is low and it will be, I mean that's what the model is saying, the prediction will be low. Okay.
So confident, the model is more confident about a point will have like very short improvement.
Depends on, now let's look at a slightly different case. Let's look at the first point. Okay. The first point, the confidence interval is small, but the predicted value is large. Okay. So for this case also expected improvement is slightly high. The reason, model is saying that I am confident that this value will be large. I mean the band gap will be large. Okay. So the way to see this thing is that you have to look at both confidence as well as the mean value. Both of them together will tell you the value of this expected improvement. If the mean is large and confidence is also large, the expected improvement will be, I mean it will be on the higher side. And if you are confident, let's find this case, if you are confident that the value will be low, then expected improvement should be low. In some cases where the uncertainty is very large, but the mean is less, then also expected improvement will be high. Okay, so both the things you have to look together to be able to know when the expected improvement will be large. Okay. Now, given this, what we will do next is we will select the candidate with the best expected improvement. Okay. So I run this code. Now I have expected improvement for all candidates. I simply select the candidate which has the best expected improvement. So now so this is the candidate that was selected, lanthanum fluoride. Okay, LAF3 got selected. So now for this LAF3, what should I do next? I have selected it based on expected. What should I do next? Yeah, so I need to perform experiment. My experiment could be actual lab experiment, it could be DFT experiment, whatever it is. Okay. So, so next we do the experiment and find the actual value. Okay. So when you did the experiment in the lab, this is the output you got, 6.6. Okay. Yeah, you can do. Yes, you should now start doing that. Yeah. But in this case, the thing is, yeah, I mean, that part is understood that somewhere you went ahead and did the experiment and got back this value. Okay. Now, this 6.6, is it the predicted value or the actual experiment value? This is the actual experiment value. We almost don't care what was the predicted value, to be honest. Okay. The predicted value could have been 3, could have been 4, whatever it was. We have selected this. Based on the selection, we did the experiment and we found this to be the value. Now once I have found this value, I can add it into the training data. So instead of 25, now how much we will have? 26. So that's what we did. Next, we add that data point to training and we delete that LAF3 point from the candidate pool. Now the candidate pool also go 1 minus, right, because you have already done one experiment from there. So that's why the size of the training data is 26 and this decreases by 1. Okay. Now what I am doing next here is I am, so this way I need to keep on doing, right. So I have written a code which is essentially the same code, but I am repeating it 50 times. Okay. So number of times I am doing my active learning iterations is 50. Okay. So now it will take some time. So you can see step 1 was training the model, step 2 evaluate expected improvement, step 3 is your select the best candidate based on expected improvement. Then you go ahead and perform the experiment, update your training and candidate dataset. So every loop it is now telling me which are the candidates which are selected. Okay. And this is the plot. This plot tells me that in every experiment that I did, what was the actual property that I got from that experiment. I'm not, nowhere I'm plotting the predicted property, I'm just directly plotting the experimental value. Okay. And what you will see is the maximum, once we run this thing, the maximum value of band gap that we found was 11.7. So much larger than 3 electron volt that we started with. I also just checked out of the, we ran it for 50 times, right. So out of these 50 experiments, how many are better than the first training data point we started with. So around how many are greater than 3.2 whatever that value was. So out of 50, 28 actually resulted in better candidates. And at which experiment I found the best candidate is the 11th experiment. Okay. So basically this was my current, this was my best when I started my experimentation. You will find 28 points which are above this black line. In total 50 experiments have been run, and the 11th experiment is the one which resulted in the best band gap value. Yeah. Fixed value meaning? Yeah, each time we have to include no, depending on the compound or the material it identified, the value will change. So for example, you will see here. So first time it selected this calcium, germanium, okay. The experimental value of this turned out to be so low, only 1. From data, yeah. Second time it selected this was the value, okay. So this way it is telling.
Whenever we are updating the training data set, student train the model from scratch or we can fine tune it. It is a heavy model.
Very good. So in this case we are training from scratch. If your model is extremely heavy, then you can fine tune.
So we might have to.
In fact, there are some algorithms which are only meant to exploit this fact that they can be easily updated. Okay. So there are few models that allow they allow that they can be easily updated once more training data becomes available.
So if we are fine tuning, maybe we have to increase the base size, right? Because adding on only one training data may not be able to update the fine tuning.
Yes. Yes.
Is it so that the heaviest model is the best predictor, or
Predictor meaning accuracy?
accuracy and
Yeah, so it's I mean there is no fixed answer to your question, but what has been observed is the larger the data sets, the neural network models, the ensemble methods win. The smaller the data set, this GPR SVM, these type of models generally perform better. These are the observations we have. There is no proof that this, for this data set, this model will perform the best.
So on a data set we choose, go through the models and whatever is
Yeah.
there.
Yeah. So unfortunately, we have to try out all models. We have to try hyperparameter tuning, everything we have to do to know which model way works. There are general thumb rules, but it's not necessary that thumb rules will be obeyed. Okay.
Cannot we go with the reinforced learning in this case?
In this case, reinforcement learning means that there is an environment, and that environment will give reward or punishment. Okay. So in this case, how are you imagining a reinforcement learning environment will be set up?
Like with the performing experiments, come close to it, whatever is predicted, you reward it. Not close to it, then you punish it. With the experiment.
Yeah.
That I can.
Yeah. So if that's the way you are setting it up, it will be very highly inefficient. Okay, because reinforcement learning methods inherently need more amount of data to be able to start learning. And that's the whole point, right? We want to minimize the number of experiments. We want to quickly reach that point. Okay. So we can set it up like this, but you will see that it will take much more iterations to learn this thing. Okay, so this is our expected improvement iterative loop, and then next we do the same iteration loop but only with exploitation. Okay, so what will I do for exploitation? For exploitation, the only thing I will change is I will select my best. Everything else remains the same, except the best candidate that I am selecting is now based on maximum predicted y cap. So whatever band gap prediction is there, I select that candidate which has the highest predicted band gap value. Okay. So compare this thing to what we were previously doing. So in the previous case, we had based on maximum expected improvement. Okay. So now we have just simply changed that line and made it based on maximum predicted band gap value, and you rerun this thing, and this is how the results will look like. Okay. And I'm again plotting the same thing. How many experiments out of 50 resulted in a value greater than that the starting best candidate, which was around 3 EV. What was the maximum band gap that was found? At what experiment I found the highest band gap component material. Then again same loop but with exploration, and in this thing the thing that has changed is I am selecting based on uncertainty, whichever candidate has the highest uncertainty. Okay. Same thing we run again 50 loops and see how the plot comes out to be. You can see that many candidates are not doing better than the starting best candidate. There are few candidates that were found, and in this case also out of 50 only 7 were better, and it actually did manage to find the best candidate, which is, so in this particular data set, that 1600 data set, 11.7 is the highest expected, 11.7 is the highest band gap value. Okay. So you cannot do better than this because your candidate set best value is itself 11.7, so you cannot find something better than that, right? So and last, because it's for all those 1600, in this case the calculations are, the experiments are already done, but in reality it will not be available. Yeah. And then lastly we have a random selection, and in this case what I do is I just simply select, in every loop I randomly select one of the candidate and then do it. Okay.
Sir, one more question.
Hmm.
Like, how do we define the candidate space? Candidate space.
Yeah, so in the way we are doing this thing, the candidate space should be defined first. When you are defining your problem statement, at that time you have already defined your candidate space.
Varying some composition or something.
Yeah, varying some composite. For example, the slides that we had, they had said, right, barium, this much strontium, these were barium, calcium, this is. And see how they also defined, I have total 6 lakh possible experiments. So the entire space was already mapped before we started doing this.
Can we do this in a undefined space which has no bound maybe?
See, when your candidate, you will be making predictions for a candidate space, right? I mean, that's a good question. You are making predictions on candidate space. If the space is unbounded, I mean, you can keep on making predictions, right? So,
We are
some.
trying to build a database for a particular application,
Hmm.
and then we can keep adding those data maybe, and it will keep growing.
Yeah, but still, where to do the next experiment, some boundary should be there, right? So, for example, in that case, the previous, say I'm talking about just nickel titanium alloy. I do know that atomic fractions have to vary between 0 and 1. It cannot be negative. Okay. So, such type of boundaries may always be present.
Maybe some physics boundaries will be there.
Some physical boundaries, some practical realistic boundaries. Say I'm talking about pressure, say some processing conditions, some temperature. There is a limit to what temperature my equipment can go. Okay. So, some practical boundaries, some physical boundaries, some things will always be there. Okay.
And inside those boundaries, you can take some random sample also and can do this experiment. Right?
Yeah, you can do through random selection also you can do. But in this earlier, in this case the candidate space is defined. It's not even grid search. Some materials are defined, from that I want to select. Okay. You can have in those cases, the electrorestrictive coefficient publication, it's a grid search, right? I will vary my concentration is say step size of 0.1 and then do it. There are a lot of variations you can bring to it, right? For example, first I'll start with a grid size which is step size of 0.5. So, very coarse grid. Some things which are selected, then I'll make it finer. From 0.5 now I'll make it 0.1 and then do more search. So, all these variations can be introduced. Okay. So, for this case, random search only 6 out of 50 resulted in better, and the first random search itself actually resulted in the best case. Okay. But anyway, so we want to compare these 4 acquisition functions, and this is how the run of all 50 experiments for all those 4 acquisition functions look like. So, let's next I have plotted a distribution plot for all 4 of them, and now let's try to understand it. Okay. So, this is how the results look like. Now, you guys tell me which of this method is better, expected improvement or exploitation or exploration or random search.
Expected improvement will be better.
Okay. So, why is it better?
Most of the cases it is giving higher values.
So, if you see the best value from expected improvement, exploitation and exploration, all 3 of them, the best value is I think 11.7 band gap, which is the highest band gap. So, actually all 3 of these approaches were able to find the best possible material. So, on that parameter, all 3 of them are good. Okay. Now, features are same. In fact, the model is, GPR model is the same, the code is the same, everything is the same, nothing different in terms of features.
So, in each experiment it is able to find a higher value of band gap. In each experiment.
In each experiment, it is able to find
A
higher value than the best. Okay. So, if you now look at, I'll try to make it slightly smaller. what happened? Something happened. Yeah. So I want to bring it in same plot, same frame, but I am not able to do it. Okay. So maybe you guys can. Yeah, I'm doing. Where is this thing? Okay, let's see if I can. Something is stuck. Okay, so the top one is expected improvement, this one is exploitation. So if you see the distribution, on the x-axis is my band gap. So if you see the distribution, which of them are resulting in more candidates with higher band gap? Exploitation. Okay, exploitation is giving much more candidates which have higher band gap as compared to expected improvement. Okay, so on that parameter, exploitation is better. So out of 50 experiments, how many experiments resulted in larger, on an average? So a better way to say this would be, on an average, exploitation gave me candidates which are say around 6 or 7 EV, while expected improvement on an average gave me candidate somewhere around here, right? On an average, this is the output of the candidates. So in that respect, exploitation is better. Okay. Yeah, and then explore is actually pretty bad, right? Explore is giving me candidates which are very low in band gap. So in this parameter, exploration is not good. But exploration did find the best candidate, right? This is my best candidate, the one with 11.7 EV band gap. And expected improvement also found it, exploitation also found it.
Density as in the number of.
Yeah. So what about which of this method is most efficient?
Expected improvement found a distribution which is kind of equal throughout all the band gap, but they are kind of centering around some particular.
Yeah. So that's also a good observation. Expected exploitation is resulting in slightly higher average band gap. Exploration is resulting in lower band gap. Expected improvement has uniform, so almost like uniform distribution across the entire band gap space. But my question is, see, you have to remember why we were doing all of this. We wanted to efficiently search for the best candidate. So what is the meaning of efficiency here? Lowest number of experiment to find the best candidate. So which of them is doing that? This plots will not tell you efficiency. So you have to look something, read the hands-on session and check. Okay, I think this plot will tell you. So the maximum band gap value is this one. Okay, the blue point, the blue one is the one which found the best candidate in the lowest number of iteration. Okay, almost around 11th iteration. While exploitation or exploration, they found it slightly later. So if say every experiment was costing 1 lakh rupees, okay, so this is the difference in the savings. Okay. Yeah, so that's another good point. Is it always true, or only for this particular data set, only this candidate set it happens so? What do you guys think?
Shouldn't be the case always because experiments record property
Particular data set only.
Yeah, so this behavior that you are seeing, that at the 11th experiment and so on, obviously it's for this data set, but on an average, expected improvement will do better than your exploitation or exploration. Okay. So this thing has been, the different acquisition functions have been tried for different material data sets, and expected improvement and exploitation, though both of them seems to perform well, and expected improvement always performs slightly better than exploitation. So this observation has been made. Why should it happen? Why expected improvement will always perform slightly better?
Why it is so?
Sorry?
I want to ask the same.
Okay, but I want to ask the same question.
Data is well spread out.
Okay, so we checked, right? We have to go back to the last lecture. Expected improvement does both things, exploration and exploitation both. Okay, and because it is doing the both thing, it will never get stuck in some sort of local minima maximum. It will always find your uncertainties will always guide the model to look into newer regions, which will allow it to find new compositions or possibly better candidates in those search spaces. Okay.
We are going to combine all of this. Like we are selecting a batch, right? Each of the candidate we can take one best from each of the methods. Then is it going to improve the efficiency?
Yeah, so that is more for comparative performances. That is not from a, I mean, you can compare the efficiency of across all four as well using the same thing, but most efficient method would have been just using expected improvement alone. Why to waste your effort in random search? Okay, because if you see, right, random search is giving always almost low band gap thing. So we are wasting our effort if we are using a random search also as part of my experiment. Okay. Okay, so now let's cover a few more aspects here. There are a few more details here. So already someone said, right, exploitation has distribution shifted on the right, high band gap, exploration on the left. Okay. What happens if you combine the distribution of exploration and exploitation? Okay, you will get something like this. And this thing clearly tells you how exploration, exploitation are being combined in expected improvement. Okay. Yeah. And just one more thing. What is random search telling you? The distribution of random search? Yeah, so most of the data is in this range. So this is random search is actually representative of the actual distribution of the data, right? So if an algorithm, the different in this distribution versus this distribution or this distribution is actually telling you the machine learning method's performance, right? Because of the machine learning, you are able to go away from a random distribution to a more knowledgeable distribution. Okay. So I mean, there were so many concepts we covered, right? First of all, see, EI distribution is not always good. I mean, that's another point you should remember. Expected improvement not always tells you good candidates. It will also tell you bad candidates. Why does expected improvement tells us bad candidate? Because it does both. It does exploitation as well as exploration. Okay. When it's doing exploration, exploration is like a very risky investment. Okay. If you do, if you put your money in risky investment, it can go either way. But does it mean we should stop doing risky investment? That's also not a good strategy. You can, I don't know how many of you have financial advisors, but that is also not a good strategy. We should always spend something in a risky investment because the returns could be extremely good. Okay. This is what expected improvement is actually doing. Okay. This is your mutual fund which has all types of investment. It has some high risky investment, some low risk investment. Okay. So some place it is exploiting, some place it is exploring, and not always, not all your stocks returns will be good. Some will be very good, which will overcome the losses that you will make with the bad ones. Okay. So yeah, so I think that's the best way of describing this thing. Okay. I think we should start doing it. I'm sure there are many companies doing it. Don't we have a center here for we have something at IIT Madras for financial. Yeah. Okay, and then these are some, let's see, does always perform better? What other improvements can be made in terms of model training? So you guys can think of what ML model training improvements can be made. And then I just started with 25 data points. Maybe you can start with say 50 points or 100 points and then check how does the performances changes. Okay, I think that's all I wanted to cover. Any questions?
So the more accurate the model will be, the better will be the performance, right?
The more
Accurate the models will be, the better will be the performance, right?
the more accurate the models will be, performance meaning in terms of errors.
No, in how many iterations you are getting the best?
Yeah, so this is a question which I actually don't know the answer for. It seems intuitive that it should happen, but I'm not sure if it always happen like this. So this is where I was saying there is a difference between accuracy and discovery. So I don't know. I think in some cases it may not always be the case, but in many cases it may be true.
And in that case, EIE and exploitation will be very close, right? The discovery process of EIE and expected improvement and exploitation, they will be very close because the uncertainty will be really low, right? For that case.
Yeah, I'm not sure about this again, because see, exploitation is about where the model predictions are high. Okay, where does the actual good candidate resides in the candidate space is not known a priori, right? So what matters is the accuracy of the model in that region. But whenever we talk about accuracy of the model, we talk at a very average level. So root mean square error. What does that mean? In the entire space, how is my model performing? But from a discovery standpoint, it only matters how your model is performing in that small region where the actual best candidate lives. So there are few subtle differences, and I do not have good concrete answers for your question.
Maybe what I said, like models accuracy, if they are accurate, it doesn't mean that they will have less uncertainty, right? It also depends on the architecture of the model, right? So if we have different architecture or maybe some different kind of models.
See, the uncertainty of the models comes from distance from the training data. Okay, the uncertainty concept comes from the distance from the training data. How far are you going in the feature space? That tells you about the uncertainty. Okay. Accuracy of the model comes from
Difference between
the prediction versus the actual case.
So very primitive, but can you please explain the data once that has been trained on? Like what
Yeah, it's a band gap. Okay, yeah. So features, we can go through them. I think there was somewhere some features were printed, right?
It's in the beginning only the trained data, line number 9. So what are the
Yeah.
individual?
So I think one of the library, just like Jarvis, there is MagPie library also. Very much similar actually. So what are the features which are here? Let's see, I want to scroll. Okay, so this is MagPie data minimum number. I think this may be atomic number. So minimum atomic number, maximum atomic number, range, mode. So all types of statistics, right? Average, min, max, mode. Mendeleev number. So there is a Mendeleev's periodic table. How many of you are familiar with Mendeleev's periodic table? Just like the modern periodic table, there is a Mendeleev periodic table. So the minimum number in that case, and then similarly other, I'm not, let's see how can I scroll there. Yeah. Actually, there was a list, right, somewhere. Okay, so this is better. So Mendeleev number, everything related to Mendeleev. So this should be some magnetic movement. Okay, so mean, this is space group number. So for a particular element in its crystal structure, what is the space group number? range of the space group numbers and things like that. So overall 132 features are there.
So would we need all of these or just even one or two feature would suffice to train a model?
So all features are needed. So once you create that function, right, for any candidate you need all m features. It should not be for one candidate you have only 10, for the other you have 132.
But it should be uniform.
It should be uniform.
Even if it is 10, it should be uniform.
Yeah. Even if the feature size is 10, you should have those 10 for all candidates. So remember, we always makes that X matrix. So X matrix, it should have entries for all my candidates. Yeah.
If the underlying model is not Gaussian,
Yeah.
support vector or even every time we have to do bootstrapping to get those values.
Yeah, you are always changing your model, right? Complete models are different.
Every loop.
Yeah. But they are not expensive. I mean, everything has to be in the context of experiment, right? If experiment is taking 3 months, one day you spend. So it's very simple, not very expensive.
And is there any combination of model and acquisition function not allowed?
No, nothing like that. No, you can try all models with all acquisition functions. Yeah, it is just that there are certain models which are more, the reason Gaussian is more popular is because there are analytical, you can compute, you know how Gaussians, multiplication of Gaussian is a Gaussian. So analytically you can compute everything. It's a closed form solution that you can write on pen and paper and then evaluate. So that's what makes it more popular. And whenever you can do such things, you have more fundamental basis. You can derive more things from these things. That's what make it more popular.
Can you also compare probability of improvement as one of the?
Yeah, we can compare. Like I didn't do it in this one. I think that should be a good exercise I can add next time. So probability of improvement can also be included here. We had a formula for that in the slide. So same thing we can implement it here. But generally people don't use probability improvement. They directly go to expected improvement.
These functions, they use the CDF and PDF of Gaussian. Do they assume any underlying distribution in the data?
Underlying distribution in the data is not, I mean, the most fundamental assumption is that a Gaussian process, GP, defines my data. This is the underlying.
But that's not true always.
So GP is something that can define any type of, GP is something like all possible functions. Okay, so it can define. That is why in a Gaussian process you can have zero training error. Your overfitting may be there, but any training data that you have, you can fit a Gaussian process to it. Yeah.
So, then my question, there were a formula column there. Have you dropped it?
It should have been dropped.
And can
Yeah.
you do one hot encoding?
Yeah, you can use one hot encoding. So one hot encoding in this case could be your 100 elements are there, whatever number of unique elements, and you just simply mark one or 0 whether that element is present or not. The problem with that would be that whether you have, you don't account for the atomic fractions, but if you want to account for the fractions, you instead of one hot encoding, you can simply put the number or atomic fraction of that particular element. That way also you can do it. You have to drop the formula column because that is not a number, right? You cannot, yeah, it's a string. Yeah. So somehow we have to convert all our strings, everything into some form of number. Which feature is it?
So Polinic featureization is given.
Okay, I'm not, I think I read this one author, right? Yeah.
Polinic, he used it for some refractory materials.
Okay,
So it is similar to nitride. It also converts into like these fundamental properties.
we can check. So OL.
OLY.
Hmm.
So OLI
Alloy features. Is it for alloys?
Yeah, it converts any composition into set of fundamental features.
Is this the one?
Yeah, I think the first one is the this is for
Yeah, I'm not able to find it.
yes, I think yeah,
This is the one?
Taylor's path preference.
Is domain knowledge
Yes.
special?
So here it has given reference for only featureization. So my question was associated to this, like how do we know that whatever like MacPy and all these things we are using, they are actually giving the correct ones. Like, sometimes these questions come.
Like whether the output feature is correct or not. Yeah. So that's a fair point. I mean, it is as simple as asking, do you use LAMPS or DFT? How do you know? I mean, WASP, Quantum Espresso, GPOW. How do you know they are giving PhonoPy? So the question is, any package that you are using, how do you know that is correct or not? So most of us do not spend time. We just simply assume. But believe it or not, there are some people who spend time, they go through the code, they check, and they are the ones who help us to know whether we are doing things correctly or not. So there will be always someone or the other who go and look at the paper. Like when I was in Georgia Tech, I know someone who went through PhonoPy code just to check whether they are doing things correctly or not. So I mean, I think simple answer is you either check yourself or you believe that someone else in the community will help you check it. Yeah, there are forums there. People do report. People report that this is the errors that they are seeing and things like that.
So like here we just compared the way we are defining best candidate, right? Based on that, how discovery process is affected, right? So there can be other things that can affect the discovery process, like the initial input that we are choosing to train the model, and also the kind of models we are using in the ensemble to get the distribution of prediction, right?
Yes.
So yeah, should we also test that, like what kind of distribution of data we should take initially that will give us good discovery process or efficient discovery process.
But so your point is valid. Your type of models you are using, the type of initial distribution that you have, all of them will have an effect on the efficiency process of discovery. But the initial data set is something which you do not have control over, right? That much control over. Whatever data is available, that's the data that is available. The other point being what type of models to use. So generally what people do is they'll within the training data they'll do something like cross validation, training test split to know which is the model which is more accurate. So GPR accuracy versus neural network accuracy versus gradient accuracy, these are the things they'll check. Whichever results in good accuracy or the best accurate model, they go ahead and do the active learning strategy with that model. That is one thing that people do. There is another thing that people sometimes do, not more. I mean, some groups have only done it. Say the initial data set was 30. From that 30, they kept aside 15, not even 15, say they kept aside 20. They started with 10 and they assumed my candidate data set is this 20. Now with this 10, which is the model which is resulting in the best candidate from those kept aside 20 points. So they made a very smaller candidate set and they checked which model is able to now efficiently find within that candidate set. Okay. Whichever model does the best job of efficiently discovering it, they use that for the actual iterative loop wherein the whole 30 points are now your training data set, and then your whatever is your candidate set, actual candidate set is the one they use.
And let's say for in the perspective of data points, let's say we have millions of data points as candidates and we want to build an initial data set So is it a
Hmm.
good idea to randomly randomly select?
So you have to use Latin hypercube sampling, or there are more sampling approaches. So that is what I'll recommend. Don't randomly do it. Use some more like Latin hypercube sampling based approaches to do that initial sampling.
Make it more sparse, right? Like make it more spread it across the space, right?
So that's what I'm saying. Latin hypercube sampling, these are the algorithms that you want to use for such things. Okay, any other question?
In this case, it is only one Y we are talking about. We have
Hmm.
multiple Y values.
Very
Then
good.
the optimization will be little bit
Yeah.
how to proceed on that.
So there is a multi-object, so that goes into multi-objective optimization. So there are algorithms for that as well. The expected improvement that we talked about today, the expected improvement has next, I mean it has been developed even for any number of dimensionality. The meaning, no matter whether you have one property, two properties, or how many ever properties you have, the expected improvement formulations for that thing is also available. So that is something you can check. Whenever we talk about multi-objective optimization, one very simple thing that people generally do is they weight the different properties and then make a objective function that is a combination of all the different properties you are interested in. Another the way people do it is they look for a Pareto front. So you look for those candidates that move your Pareto front. Okay. So there are some algorithms around that. So there are no like depending on the problem, there are mathematical formulations available. Although in research, I have not seen very good. People do use it, but it's not that very at a very good advanced level they are doing it. Theory is actually much more advanced level available, but implementation wise people are not using that difficult theories so far. Yeah, it is there, like I can tell you. I mean, the way it happens is that you talk about expected improvement. So two, let's say parameter space is 2. So now instead of my Gaussian being one dimensional, my Gaussian itself is 2 dimensional. So 2 dimensional Gaussian is like a bell. Okay. So now I can talk about expected improvement in one direction and expected improvement in other direction, and then you have the integration happening in this 2-dimensional space. Through that you can do it. Yeah, I mean this itself is, or whenever I have, so Gaussian process is entire foundation on joint probabilities only. Joint conditional probabilities, that's how entire formulation is. Yeah, so I can share one book with you. There's some, I'm not engineering, surrogate modeling of engineering design. I can share that with you. I'll share the book. Yeah, so if you guys want anything, always feel free to write to Vijit and Abhijit. You have their contact details. So feel free to write to them and then we'll try to help you guys. So did you guys enjoy the course? So thank you so much. Yeah, with that I think we'll end.